Hello my dear, welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat, Faculty Department of Mechanical Engineering. So already we will discuss that with what is the energy balance, what is the entropy balance and what is the exergy balance. Now throughout all this we have to come with a common platform. What is that? We have to already will see that if there is a system and that system, if there is a displacement of a boundary, that system, if this displacement of a boundary and that displacement of a boundary under quasi-equilibrium process, mind it, the displacement of a boundary under quasi-equilibrium process, in that sense, the work transfer is a reversible work transfer and that is your integration P dV. Okay. Now, the limit of integration P dV, it is not a section, it is a point. That means state property point 1 to state property point 2 and you can integrate, you can find the work transfer reversibly. And that work transfer is known as thermodynamic work transfer. It is a not kind of mechanical work transfer. I'm telling you, it is a kind of thermodynamic work transfer. Why? Because in this work, there is a resistance force is involved. Now, we have to start with the another work transfer that is related to the control volume system. That means if there is an open system and there is a something in and something out with respect to the change its property within the system, or you can say the steady system. So, during that, what is the work will developed by the system or work can absorb by the system. If the work developed, you have to maximize, and if the work absorbed, you have to minimize, then it must be, you can consider the internally reversible. That means the process is internally reversible. So mind it, beta, what I have derived the work from here with respect to the control volume, that work is a internal reversible. That means irreversibility within that system we can neglect. So in that sense, if there is a work output device, that gives the maximum work, and if the work input device, that gives the minimum work. Okay. So if we take a control volume, beta, if we take a control volume, my dear, so this is your control volume. Let's suppose this is our control volume. Any control volume is there. This is your control volume. Okay. Let's suppose this is your control volume, and this control volume have many inlet and many exit. Have control volume have a many inlet and many exit. That means this is your control volume, have the inlet. This is your inlet. Let's suppose this is your inlet and this is your exit. So this is your control volume. Okay. This is your control volume, and there is a control surface is there, and we assume that the property at this cross section. So this is the inlet cross section I, and there is exit cross section E. Mind here, today class is very important. Why? Because 99% student get confused here, okay, sir, what is the nature of this work? So this work, and we assume that there is a heat transfer. There is a heat transfer through a with a thermal energy reservoir at Q, and in this sense, there is a mass in and there is a mass exit, and the system, mind it, we take the system as a steady device. Okay, so in this sense, there is a work out, and that work, this is your work. This is the work out, okay, heat transfer, and there is a work out transfer. So this is our control surface. This is our control surface, and during the fluid in and fluid out, there must be a transfer of energy. So we have to, what is the balance? We have to balance the entropy. If we balance this entropy, that means mass across the boundary, and this is the surface temperature. Let's suppose this boundary have a surface temperature T. Why? Because when we have defined the entropy balance, you have to also the transfer phenomena of heat. So if heat divided by the temperature, with temperature across which the system boundary temperature, that means the temperature at the boundary across which the heat will transfer. So if we balance the entropy of a control volume, already discussed this thing, entropy balance for a control volume. What is the entropy balance for the control volume? Entropy in minus entropy exit plus rate of entropy generation, don't write a rate, plus entropy change of the control volume, that means delta S of the control volume. This is the entropy balance. Now this entropy transfer, this is the entropy transfer due to heat and mass, due to heat and mass, and this is the entropy generation. This is the entropy generation, and that is the entropy change of the system. Okay. Now, so if we take, there is a heat transfer Q divided by, let's suppose rate basis, you have to write a rate basis, no problem. So if you write a rate basis, so this is your d by dt. You can better write like that. Okay. So dq, and what is the surface temperature T? This is your in plus mass is in, so m dot I SI. Here is a specific entropy SI. This is in. What is the exit? Exit is, so entropy exit is only related to the heat and mass, not work. So exit is m exit, S exit, okay, plus entropy generation is equal to dSCV by dt. Okay, no problem at all. This is the entropy balance. Now this is our main equation in the general for the control volume device. Now beta, if the control volume is a steady device, so that steady device, that means this is 0, this is 0, that means steady device. Steady device, okay. This is your steady device. So we can write like that. S generation is what? S generation is, so S generation, that is the rate of entropy generation. This is equal to ME SE minus MI SI, and this is your minus Q by T. That's it. This is your entropy balance, and this entropy balance is for the steady device. This is for the steady device. Now my dear, this is the steady flow device. Now for the single stream, so for if the single inlet and single stream, that is called single stream, and for single stream, so for single stream, what is that beta? Summation of all inlet is equal to summation of all exit. Why? Because steady also, and single inlet, that means what is the MI, single inlet and single exit, that means one inlet, single stream, that means one inlet, one exit, one inlet and one exit, one inlet and one exit. In that sense, what is the S generation? What is the S generation? Is equal to, you have to common the mass m dot into, what is that? If you common SE minus SI, SE minus SI minus heat transfer divided by T. This is for the single stream. Okay. Now my dear, if we take say third situation for the adiabatic device, that means adiabatic device, if adiabatic device, there is a no heat transfer, so this is what with the heat entropy generation, this is equal to m dot into SE minus SI. That's it. So this is the entropy. This is the very concise manner. What is the assumption of this one? The assumption of this one is, sir, the device is steady. What is the assumption of this one? If the entropy generation is equal to change in entropy of the inlet and exit, that means steady device. Next, single stream, third one is adiabatic, third one is adiabatic. That's it. This is the assumptions, this is the condition. Under this condition, this equation is valid. Okay. Now if you take one thing, that means reversible adiabatic, that means if you take a note reversible adiabatic, reversible, why? Because we have to go with through the reversible manner. So reversible adiabatic, reversible plus adiabatic. So my dear, what is the reversible? In this reversible, entropy generation is 0, and in the adiabatic, heat transfer is 0. If you combine, so adiabatic, so what is that? M dot S exit minus S inlet is 0. That means what is the exit entropy is the same as the inlet entropy. That means for the reversible device, if the device is a reversible, there is no any entropy at exit and inlet will be changed. That means the entropy, what is the entropy due to the mass will in at the inlet section is the same as the entropy that is the mass which is exit from the exit section when there is a reversible, always as well as there is a adiabatic. So we have to apply this equation. So what is this? What is the condition of this equation? This is very important, I am telling you. What is the condition of this equation? Now, what is the condition? Steady device, second, single stream, third, adiabatic, fourth, reversible. So this is the condition under which this equation is applied. That's it. Okay. Now, my dear, if we take, that means now we have to go with some subtle concept with that. What is that? See, my dear. See this one. Take any process, take. This is very important, I am telling you. This slide, from this slide, this is very important. All the previous slide you have already studied. Okay. Now, take steady flow. Steady flow. Flow is steady plus reversible process plus adiabatic plus single stream. Okay. Steady flow, what is the mean by the steady flow in this condition? The entropy change within the control volume with respect to time is equal to 0. What is the reversible in this process? That means entropy generation is equal to 0. What is the adiabatic? That means heat transfer is 0. What is a single stream? That means summation of all the mass at inlet is equal to summation of all the mass at exit is equal to m. That's it. This is the 4 condition. Okay. Now, under this one, what is that? Then, just now we have seen that entropy exit is equal to entropy inlet. Yes or not? Entropy exit is equal to entropy inlet. This we have to say. That means if there is a control volume, and this control volume is under this condition, so what is the entropy at inlet and what is the entropy at exit are same. These two are same. Okay. That means now, so this is okay. Now, if this control volume will produce a work, we have to take per unit mass here work, no problem. So entropy inlet is small, no problem. So work will develop a work and this will take a heat, no heat. Okay, there is no heat. Adiabatic, that means no heat, only producing a work. Now we have to find this work under this condition. Okay, we have to find this work under this condition. Let's suppose under this condition we have to find. So beta, we have to apply a TDS equation. TDS is equal to dH minus VdP. This is a per unit mass. This is a per unit mass. So better you can write a small. Okay, this is a per unit mass, specific. Now, reversible adiabatic. Reversible adiabatic, that is, or that means change in entropy, it is 0. Why this is 0? And now beta, this equation, under which condition this equation is applied? You know this thing? Under which condition this equation is applied? You know this thing? This is for any process. Any process. Any process. Either reversible or irreversible. Why? Because this is a state property. Now, entropy inlet is equal to entropy exit. That means this is 0. This term is 0. Why 0? Why? Because reversible. Reversible plus adiabatic. And we know that reversible plus adiabatic entropy is 0. So, what is the dH? Enthalpy change is equal to VdP. This you know. Now my dear, so if we integrate from inlet, this is inlet cross section I, and this is exit cross section E. So if we integrate this one, that means H exit minus H inlet is equal to integration I to E VdP. So VdP, so this is your change in enthalpy. So now what is this VdP? We'll have to check it. Okay. Now, so this is according to, so this is according to this, from where you can find entropy balance. Entropy balance. So entropy balance for this condition, and this is your TDS equation. Now we have to apply third equation for the control volume under the steady state. What is that? Steady flow energy equation. So what we know that steady flow energy equation for this system, very important. So in general, what we know that steady flow energy equation, what we know that, and steady flow energy equation is what? This is your first law, mind it. First law of thermodynamics of control volume system. Control volume system. Of control volume system. Now, what is that in general equation? What is that? Q dot plus M dot I H I plus V I square by 2 plus Z Z I, okay, is equal to, what is the work transfer plus exit in mass at exit, enthalpy at exit plus velocity at exit k square plus Z Z A. Okay. Now my dear, if we neglect the change, in kinetic energy and potential energy, that means we have to check that we have to take, there is no any change in kinetic energy, that means there is no change in kinetic energy, that means there is no any increase or decrease the kinetic energy potential, that means we have to take change in kinetic energy and change in potential energy is equal to 0. That's it. So this you can neglect. Okay, we can neglect. Okay. Now the system is adiabatic, so you can take a 0. So what is the equation? That means M dot I H I is equal to W dot plus ME dot HE. Okay. Now for the single inlet, single exit or steady device, that means M dot I is equal to M dot exit is equal to M dot. So what is this beta? If you divide this one, if you divide this one, yeah, you can take also kinetic energy, potential energy change. You can take, yeah, why? Because there is a steady device, and if there is a nozzle, so there is a change in kinetic energy. If there is an inclination, so in general you can take, no problem. In general you can take. So this is for more precise equation. If you take, but in general we have to take, we don't bother about that one. That means we have to take this one, no problem. First we have to take this problem. That means we have to take. That means initially this is a special case. This is there, no problem. This is okay. But after that we can assume for that one little bit. That means you can, right now in general we have derived the general equation. So in the general equation you cannot neglect. Okay, you G Z E. Okay, you can take, no problem. Now, but this is 0, adiabatic, this is 0, no problem at all. Now, what is that? There is a single inlet, single exit. So we have to take that one. That means Hi plus Vi square by 2 plus Zi is equal to this work divided by mass flow rate, you can take, plus He plus Ve square by 2 plus Ze. This equation is applicable at the section, not at a point. So my dear, what is this one? This is what? This is your specific work. This is a specific work per unit mass. Okay, this is your specific work. So what we can write here? Hi minus He, yes or not, plus Vi square minus Ve square by 2 plus G Zi minus Ze is equal to 0. Yes or not? Yes or not? Now my dear, see this one. What is this? We have to calculate change in enthalpy is what in generally? So we have to take change in enthalpy. That means from here, if we take right like that, Hi minus He, this is equal to minus I to E V dP. Yes or not? Minus. So put here minus integration I to E V dP. Okay, this one. So now my dear, this is what? That means there is not 0 here, not 0. This is your W, and this is in the condition reversible. That means, see my dear, if you take, this is your reversible process, na? We have to apply this one for the reversible process, na? This is for the reversible process. How will come? This is for the reversible process. So this is your reversible. This is your reversible. Okay. So what is the equation for the reversible work? Is equal to minus I to E V dP. Initial minus final. Initial minus final. So change is final minus initial. So minus per unit mass delta Ke minus delta Pe. This is per unit mass basis. So this is the work output from that device in the reversible manner. So this is what, beta? What is this? What we can write? This is the reversible work output. Reversible work output. This is your reversible work output associated with an internally reversible process and internally reversible process in a steady flow device. In a steady flow device. This is very important. Now, so this just now we have to see this when this equation is derived. When this equation is derived, the equation is derived when we have to assume the system is adiabatic. So this is for the, we take the steady flow, reversible process and adiabatic single stream. Now we have to change this adiabatic. We have to take second situation, situation number second, steady flow, reversible process, isothermal single stream. Now there is isothermal device. That means the temperature of the surface of the device doesn't change. That means the isothermal. Okay, that means what is the inlet temperature is the same as the exit temperature at the boundary. So boundary is isolated. So we have to take, this is very important. So this is first situation. Now we have to take a next second situation. Take, this is the second situation. Take, what you take? Take steady flow, plus reversible process, steady flow, reversible process, plus now isothermal device plus single stream. How to find the reversible work? Now we have to find the reversible work. When the system, now the system is isothermal. That means the process is isothermal, not adiabatic. Previously, we have to assume the system is adiabatic. So this is your equation. Now we have to assume the system is isothermal. What is the reversible equation? This is very important. See, my dear. So this is, so what we know that for the isothermal, we know that what is the entropy balance? S generation, rate of S generation is equal to m dot S exit minus S inlet, yes or not, minus heat transfer by T. It is not 0. See, my dear, this is the entropy balance. See this one initially. This is the entropy balance. See this one. S generation m dot Se minus Si q dot by T. This we know that already. We have to prove this one. So this is what. Now apply this equation under this condition. So this is your. Now this is for a reversible process. So this is 0. Generation is 0. Why 0? Why? Because reversible. Okay. Now what is this? This T is what? Temperature of a system boundary across heat will transfer. This is what? Temperature of the system boundary. Temperature of system boundary. And this temperature is constant. Mind it. Why? Because, why constant? Why? Because isothermal. That means you have to transfer, now you have to transfer heat. That means this is your system, control volume, and now you have to transfer SI, SE, work transfer, reversible, and there is a heat transfer Q, and that heat transfer through a system boundary temperature T, across a system boundary temperature T. Now, what is the TDS equation then? TDS is equal to dH minus VdP. My dear, this, in this case, this ds is not 0. Why? Because this is not reversible. It is a reversible, but it is not adiabatic. So reversible adiabatic is an isentropic process. Reversible isothermal process is not isentropic process. So this is not 0. So you have to integrate totally. That means you have to integrate from inlet to exit TDS. You have to integrate inlet exit ds. You have to integrate inlet exit VDP. Okay, this is your dh. This is your dh. This is your dh. Okay. Now, so what is this equation? T is constant, yes or not? So T is outside. Why? Because this is constant. So what you can write? T SE minus SI, this is specific, is equal to HE minus HI minus, you can not, why? Because volume is not constant, so you cannot take integration, VDP. Still, you have to must be a knowledge about the relation between Y, because V is not independent here, V is dependent with respect to P. So this is your equation while we are applying the TDS equation. Now, so this is the entropy balance, this is your TDS equation. So in this condition, reversible isothermal process, this is your TDS equation, okay? This is your TDS equation. Now you have to apply the first law of thermodynamics for a control volume system, okay? So you have to apply steady flow energy equation. You can apply. Why? Because steady flow. What is that? Q dot plus M dot HI plus VI square by 2 plus ZZI is equal to W dot plus M dot HE plus VE square by 2 plus ZZE. Now you have to divide this mass, and here Q is not 0. So this is your Q is not 0, my dear. So what we can write instead of Q? See this one. What we can write instead of Q? You can write Q is equal to, from here, if you write, what is Q dot? Is equal to M dot T SE minus SI. Yes or not? So this is heat transfer during this one. So put this one here. So here we can put M dot T is the isothermal, S exit minus S inlet. Okay. Now what is this one? S exit minus S inlet. S exit minus S inlet is what, beta? S exit, that means you have to put this value, that means here you have to this one, T S exit minus S inlet, T into S exit minus S inlet, T into S exit minus S inlet is equal to HE minus HI minus integration HI plus to I to E VDP. Put this one value. So from here we can put HI minus HE, HI minus HE, this equation, minus I to E V dP. Okay. So this is your this equation, and put this mass here M dot. So you this is your equation. Now so just you have to separate this equation. So M dot HI HE minus integration VDP plus M dot, you can write all this thing. So if you write this thing, what is that? M dot HI minus HE minus integration I to E VDP. So this is your Q. This is your Q plus M dot plus M dot HI plus VI square by 2 plus GZI is equal to this work transfer plus m dot HE plus VE square by 2 plus GZA. Yes or not? Now, my dear, divide by mass. So, if you divide by mass, so this is what? If you divide by mass, this is S exit minus S inlet, S exit minus HE minus HI, HE minus HI beta. This would HE minus HI. This would HE minus HI, HE minus HI, HE minus HI. Very important. Okay. So this would HE minus HI. Okay. So HE minus HI. Now divide the mass. All the mass is divided. So this is your what? HE minus HI minus integration I to E V dP plus HI plus VI square by 2 plus GZI is equal to this W dot by M dot plus HE plus VE square by 2 plus GZA. Okay. Now this is what? A specific work. Again, this is what? Specific work, and this is reversible. So this is W reversible work. Okay. Now this HI and this HI is cancelled. This HE and this HE cancel. See the beauty. See the beauty. Okay. So what is this? So this W reversible is what? Minus HI E to E VDP. So if you take this is your, so plus VI square minus VE square by 2 plus ZI minus ZE. Okay. Now you have to take a negative. So what we can write? See the beauty. I to E VDP minus delta KE minus delta PE. See the beauty. What is this, beta? That means this reversible work is independent of the process. That means if you draw the reversible work, if you draw the reversible process, that reversible process is a thoughts of a infinite isothermal, reversible isothermal, reversible adiabatic, reversible isothermal, reversible adiabatic, reversible isothermal, reversible adiabatic. And if you join this all the locus, that is any other reversible process. That means this is the reversible work associated with the internal reversible process in the steady flow, and that means both equation, this equation, see the beauty, this equation, this is the equation A and this is the equation B, and this A and B equation, A equation is for the reversible adiabatic and B equation is derived with respect to reversible isothermal. That means these A and B equation are same. So either reversible adiabatic or a reversible isothermal process, that means any reversible process, that is your work transfer. That means, so any reversible process, my dear, this is very important. So any reversible process, can be conceptualized as, succession of number of reversible adiabatic number of reversible adiabatic and number of reversible isothermal. This is the beauty. That means if you draw a TS diagram, let's suppose this is your TS diagram. Now, first assume reversible adiabatic, that means isentropic. This is a reversible adiabatic. This is a reversible isothermal, reversible adiabatic, 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 reversible isothermal, like that. And you join this very small process, and you have to join this all with a single process, combined with a single process. If you join this all with a single process, this is any reversible. That means this is your, it is an any arbitrary process, any reversible process. That is the very important thing. That means if this is your TS diagram, if this is your TS diagram and you have to draw, there is a reversible process, any reversible process, any reversible process, that means this reversible is a conceptualized at number of reversible adiabatic, reversible isothermal, reversible adiabatic, reversible isothermal, adiabatic, reversible isothermal, reversible adiabatic, reversible isothermal, like that. So if you have join, that means there is any reversible cycle is conceptualized at a number of reversible adiabatic process and a number of reversible isothermal process. That is the very important thing is there. Okay. Now, my dear, hence, for any reversible process can be thought as a reversible adiabatic process and reversible isothermal process. Now, my dear, that means, it is very important thing I am telling you. That means you can say that, sir, for any reversible process, steady flow with a single reversible process, steady flow is steady flow, single stream, the work output, that means reversible, and that is your, more precisely, internal reversible is equal to minus I to E VdP minus delta KE minus delta PE. This is for any reversible process. Any reversible process matlab any reversible, either reversible adiabatic, either reversible isothermal, either reversible reversible any reversible process. Okay, so this will be defined for this one. Okay, now if we neglect this change in kinetic energy and this change in potential energy, we can neglect. That means the reversible work is equal to integration I to E V dP, and this is your reversible work associated with the work output device, and this integration limit is the inlet and exit, not the, that means reversible work output for the steady device. This is your reversible work output. So minus indicates the output, plus indicate the input. So reversible work output for adiabatic device, for steady device, for steady device, okay. Now we have two device, that means there is a one device. Let's suppose there is a one is control volume. Let's suppose this is our control volume, okay, this is our control volume. Let's suppose there is a inlet is there, and this is your exit. Let's suppose this is your exit. This is your exit is there, okay. So it look like a turbine. Let's suppose this is your turbine. So this is our control surface. This is your control surface. This is your control surface. This is your control surface, and this is your inlet section I, and this is your exit section E, and this is your control volume, and there is a shaft is there, and this shaft is rotating, and that is a reversible. That means this is your work reversible. This is your work reversible, okay. So in this is a steady flow device like turbine. Steady flow device like turbine, okay, like turbine. So in this case, what is that? Like turbine. So in this case, we have to what the integration I to E minus V dp. This is your work, and this is your volume projection, okay. This is your volume projection. Now if we take there is another system, if you take there is another system, and that system is your closed system, that system is your closed system. That system is your closed system. So this is your closed boundary. This is your closed boundary. This is your closed boundary. This is your closed boundary, closed system. And if the system will execute by the displacement of a boundary, so the work will produce boundary work, and that work, if you write, this is also reversible, and that is your integration 1 to 2 PdV, very important. So here I or E, I and E is the section, and here 1 and 2 is the state point of the system. That means this is the system. So this is very important, I to E. And in this case, this is positive. In this case, this is your negative. So closed system, this is your closed, a non-flow system. This is a flow device, flow system, flow process, and this is a non-flow process, non-flow. This is a non-flow process, okay. Now if we take the working fluid is incompressible. This is, if we take working fluid, take working fluid is incompressible. If it is incompressible, that means density is approximately constant, and we know that that density is a specific volume. That means this is also approximately. Approximately it is constant. Approximately it is constant. So if we write W reversible output term या input term is equal to I to E minus V dP. So in this case you can take outside this one, take outside this one. So this is minus V I to E dP. So this is what? This is what beta? That means minus V P at exit minus P at inlet. Yes or not? P at exit minus P at inlet. Now we have to write like that. So this is your minus, that means this is your minus P exit by density plus P inlet by density. Yes or not? Okay. So this is your W. Now we have to write W reversible. This is out. This out is what beta? This out is what? See this one? This out is what? This out is what? Integration 1 to 2 VTP, change in kinetic energy, change in potential energy. So minus integration I to E V dP minus change in kinetic energy minus change in potential energy. Yes or not? Yes or not? So what is this one? Just now we have to calculate. What is this one? What is this one? This is your minus P exit by rho plus P inlet by rho minus this is your V exit का square minus V inlet का square by 2 minus Z minus Z exit minus Z inlet. Yes or not? Now if you take part by, that means exit and take this side, inlet take in this side. So what is that beta? If you rearrange this one, so if you rearrange this one, so Pi by density plus Vi square by 2 plus Zi is equal to P exit by density plus V exit square by 2 plus Z exit plus W reversible out. Yes or not? Yes or not? So see my dear, this is what? This is what? So you think that it is look like it is a sort of a mechanical, that means it is sort of a mechanical energy conservation equation, look like a Bernoulli equation, right? If W reversible is 0, that means we have to think like that. We have to think like that. It is sort of a mechanical energy conservation equation looks like Bernoulli's equation. Very important. Looks like Bernoulli's equation if W reversible out is 0. It is true? Question mark. It is okay or not? This is okay or not? This, see, it is sort of a mechanical energy. Yes, it is a mechanical energy. Conservation equation looks like a Bernoulli equation. It looks like a Bernoulli equation, but it is not a Bernoulli equation. Why? Because Bernoulli equation is applicable at the point, and it is this equation is applicable at the section. Very subtle concept is there. So this is not a Bernoulli equation. Note, this is not a Bernoulli equation. This is not a Bernoulli equation. This is not a Bernoulli equation, because Bernoulli equation is applicable because it applicable at the point at the point at the 2 point level, 2 points, at the 2 points 1 and 2 along a single streamline, along a single streamline, along a single streamline, along a streamline, along a single streamline. So, and this is not look like that. It is at a cross section. That means, but here I and E are not at 2 points. Here I and E are not at 2 points. So we can read here. Here I and E are not at 2 points. There are a 2 section. This is a 2 section. That means this is what? This is a control volume. So this is your in and this is your exit. So this is your I and this is your E. So this is your section, not a point. It is not like that 1 and 2 within the point. No, it is not like that. It is at the section. It is the add section, and it represents the gross mechanical energy between the 2 sections. It represents the gross mechanical energy. Okay. At the, if it is a reversible, then there is a no dissipation. So the mechanical energy at inlet is equal to the mechanical energy at exit, equal to the sum equivalent work is out from the system could be extracted. That means there is a reversible. This is a reversible process. That means there is a no dissipation. So if there is a system, if there is a no dissipation, so what this equation tells us? This equation that says that mechanical energy at inlet is equal to mechanical energy at exit plus some work you have to could be extracted from that system. That means mechanical energy at inlet is equal to mechanical energy at outlet plus some reversible work you have to out from the system when there is a no any dissipation. That means it is a work associated work if the work extraction is 0, in that case the mechanical energy at inlet is equal to mechanical energy at exit. That's it. So it is not a Bernoulli equation. Bernoulli equation, it is tells that the total energy, and that energy also in the form of mechanical energy, is equal to the total energy at point 1 along the streamline is equal to total mechanical energy at a point 2 along that streamline. That's it. But this is not a Bernoulli equation. It is a conservation of mechanical energy at inlet and exit plus some work you could be extracted. When there is no any irreversibility within the system. When there is no irreversibility within the system. So I hope you are like this video, and also you have to get a many good concepts there. In the next session we have to discuss some relevant problem about this, the application of this reversible work, and up to that you have to go through all the concept. Okay, so till now, thank you. Bye-bye.